In this video, I will go through the proof of the limit comparison test, which is really just a reformulation of the simple comparison test in a somewhat convoluted form. However, the way it's applied is very different, and its statement is a little bit different to the simple comparison test. So it's important to keep them quite distinct in your mind, even though actually this is just a sort of shortcut which relies on the simple comparison test itself. That is, the proof of the limited comparison test directly relies on the simple comparison test from video 2b. Okay, so what is the statement of the limit comparison test? Well, the first thing is that we assume we have two eventually positive sequences, so that means that beyond some point all the terms in these sequences are strictly positive, and that the sequence of fractions an divided by bn is a convergent sequence with limit L, or, special case, that it's divergent and diverges to positive infinity. So we sort of package this up into one neat statement. We say the limit as n tends to infinity of an divided by bn equals L for some L in the interval 0 to infinity, where infinity is a permitted value for L. So what this is saying is that either this limit actually exists and equals the real number non-infinity value L, or else the sequence diverges to positive infinity. That means that the sequence not only is unbounded, but also stays large forever after some point. So for every value capital M, there is some point capital N in the sequence beyond which the sequence of fractions always is greater than the value capital M. Okay, so we're allowing this possibility that capital L equals infinity, in which case we sort of abuse notation a little bit and write L equals infinity. Okay, so that's the setup. We assume that we have this defined limit, possibly infinity, for the sequence of fractions an divided by bn. Once you've got that, there are two halves to the theorem. And the first half says that if L is not infinity, then the convergence of the series Bn implies the convergence of the series An. And if you think about what's going on here, what that is really saying is that if we know that the series Bn converges, and additionally, one thing that's immediate from that is that the sequence of terms Bn must be going to 0, because we know from the nth term test for divergence that if the sequence of terms does not go to 0, then the series can't possibly converge. So on the assumption that this series converges, we know that these terms Bn are getting smaller and smaller and smaller. If this limit actually exists and is not infinity, then the sequence of terms An must also be going to 0, and on top of that, they're going to 0 as fast or faster than the terms Bn. That's really what this limit L being less than infinity means. It means that this sequence of terms is going to 0 at least as fast as this sequence of terms Bn. And so conceptually it sort of makes sense that if this is going to 0 as fast or faster than this, then if this series converges, it must be the case that this series converges as well. So that's the first part of the limit comparison test. If this value L is not infinity, then the convergence of the series Bn implies the convergence of the series An. The second part is sort of the other way around, namely if L is non-zero, but now allowed to be infinity, then the convergence of the series An implies the convergence of the series Bn. And the same sort of concept applies here as well. In this case, if it's this way around, we're saying that for this limit to equal L, then if these things are going to 0, then these terms Bn must be going to 0 at least as fast as the terms An for this limit not to turn out to be 0. Okay, so have a think about how that works, but really this is a statement about the speed at which these sequences of terms go to 0, and the fact that this comparison test holds true shouldn't be that surprising once you've understood that interpretation of this limit equaling L. Okay, but the actual proof of this theorem follows as an almost immediate consequence of the simple comparison test. It's not that tricky a proof, and I'm going to sort of highlight how it works just on this slide. In the first case, we know that because this limit is actually a defined number, real number L, and from the definition of the limit, it means that eventually there must be some point capital N beyond which these fractions get, say, within 1 of L. So you could think of this as in the epsilon comma n definition of the limit existing, we're choosing epsilon equal to 1. And these conditions here are just coming from the fact that we've assumed that the sequences are eventually positive. Okay, so in the first case there is some point n such that beyond that point capital N all the terms in both sequences are positive, and all of these fractions are less than or equal to L plus 1. And rearranging this fraction, we get that the terms An must be less than or equal to the terms Bn multiplied by the constant value L plus 1. So now we're in a situation where these Ans are all greater than or equal to 0 and are all less than or equal to L plus 1 multiplied by the terms Bn. And so just directly from the simple comparison test, if we know that the series Bn converges, the series An must converge as well. And it really is just that simple an application of the simple comparison test. Part 2 is basically the same, except there's a little bit of a wrinkle in that we've allowed L to be this non-defined number infinity, so we have to do a little extra line to cope with the L infinity case. And so I'm going to set k to be equal to L in the case where it's actually a proper number, And in the case where L equals infinity, I'm just going to take this new constant k to be equal to 1. And keep in mind that whatever k is, it's not 0, because we've assumed that L is greater than 0. Okay, and now that the proof follows similar lines to case 1, there must exist some point capital N such that beyond that point the terms an and bn are all positive. This again is just coming from the assumption that they're both eventually positive sequences. And in this case, we're essentially taking epsilon equal to k divided by 2 in the definition of this limit existing and equaling L. Or in the case of infinity, we're just saying, well, eventually these fractions stay greater than or equal to a half. Now, from that knowledge, we can rearrange that fraction and conclude that the terms bn must be less than or equal to 2 divided by k multiplied by an for all n greater than or equal to capital N. And so we're in exactly the same situation as we were in before. We can apply the simple comparison test and conclude that the convergence of this series, which we know gives us a control for the bn's, implies the convergence of this series. And that's the part 2 of the theorem substantiated. For another example of the use of the simple comparison test in proving a more sophisticated convergence test, take a look at video 2D, in which we go through the proof of the ratio test. Video 2D will be the last video I will post prior to the second workshop.